All right, here is the last video of the semester, I'm pretty sure. This one is going to be about the benefits of the different ways that we can do concurrent programming. The three different flavors that we talk about in the book and that are important to understand is process-based, thread-based, and I/O multiplexing-based. What you're doing in homework 6 is I/O multiplexing. It's kind of the hardest one to understand, but it's definitely very, very important. Like now in 2020, it's so hot right now. Like you use I/O multiplexing in lots of places. There's actually a lot of really cool language primitives that are being used to make I/O multiplexing easier than it is in 361. And you'll probably find those and you'll curse my name for making you do it the hard way. But when you do it the hard way, you actually understand what's going on under the covers. What's important to talk about first is the idea of a process versus a thread. So we have been talking about processes this entire time, where processes have virtual memory, they have a bunch of registers and stack pointers and instruction pointers and stuff like that. They have all the state that defines a running process. That's actually not 100% true. It's not just one blob. What you actually end up with is two different things. You've got the process, which has to do with what open files it has, what resources it has access to, what memory it has mapped into its address space, all that. But the state of the running program is a little different from the environment that it runs in, right? So that every process has at least one thread of control that is defined by those register values. Like what's in the registers, what's the stack pointer, what's the instruction pointer. There's nothing stopping you from saying, hey, within one process, why don't I have another thread of control that has its own registers, that has its own stack pointer, its own instruction pointer? Then I can run two different things in this same environment, and I can use more than one processor. I can handle multiple requests very easily, all this good stuff. And that is where we get the difference between a process and a thread. All processes have at least one thread of control. Every thread of control exists within a specific process. Processes can have more than one thread at any given point in time. When a CPU schedules something, like decides what to run, it's going to decide based on the thread it wants to run. And then based on that thread, it's going to say, oh, I actually need this memory mapping because it's part of this process. So if we zoom out and we don't talk about all the details, we can think about the stuff that's associated with the process is like the memory and specific resources that have been allocated to that process, like open files. Then the threads are things that get scheduled by the operating system to start running on the CPU. So threads run on the CPU in the context of a specific process. You can't have threads that don't live inside of a process, and you can't have a process that doesn't have a thread of control. If it doesn't have a thread of control, then what good is it? It's just a bunch of allocated memory that no one is going to do anything to. So when we do multiprocessing or multi-threading, what we're fundamentally doing is we're saying in the process example, we have lots of different virtual memory address spaces, and we have lots of different threads of control. Every one of these has a thread of control. Usually when you run multiple processes, they're going to be pretty separate. There's not a good reason to do multiprocessing in a lot of scenarios when you're trying to use concurrency to write parallel programs. It's usually not the right way to go. The other option is to have a thread-based system where we say, okay, I'm going to do just what I had in this other example right here. I can have lots of these threads that are working their way through the text of the program at different places with different stacks, and they can be scheduled in parallel, but they all have access to the same memory all the time. And one nice thing we get here is that when the CPU is going to choose to go from one thread to another thread within the same process, they don't need to change their page table. They don't need to invalidate the TLB. So threading in general is going to be more lightweight. It's going to be faster, but there still is this overhead of keeping track of each individual thread, having the operating system choose which one to do at any given point in time. And you also have that tricky part of any interleaving between these different threads is just as valid as any other one. So you need to use mutexes to block things, because anywhere at any point in time between any two individual assembly instructions, thread number one could be pulled off the CPU and thread number two gets put onto the CPU. That ends up being really tricky and one of the main ways that you get tripped up when you're doing multi-threaded programming. Now, the most interesting one here is I/O multiplexing. This is where we say, listen, I'm going to have one thread of control, and it's going to go through a thing called an event loop. In an event loop, what I am doing is I am taking new events that come in, and usually there's going to be I/O events, like bytes came in off of a file descriptor, or a file descriptor is able to be written to, and I am going to do whatever it is I need to do to handle those specific bytes, and then I'm going to wait for more bytes to come in. This allows me to say I'm going to have one thread that does CPU-based things, but it's only going to do them as a result of certain things happening. So when I have a whole protocol that I want to do things on, I need to refactor that protocol so that every single thing that could ever happen between point A and point B has to happen in one iteration of that loop. Let's give a little super basic example, and this is going to have a lot to do with homework 6, so hopefully this will be helpful in that way. Let's think of a really, really basic protocol like regular old HTTP. In regular old HTTP, what I do, if I'm the server, that I accept, I receive the request, I open the file that was requested, I read the file that was requested, and I write the file that was requested. So in a multi-threaded web server, what you would end up doing after you call accept, you're just going to refactor this and say handle request, and then all of the requests that you're handling. And here in a multi-threaded one, I would just do a pthread create of the handle request function with the file descriptor that I'm passing through. That's all you would need to do. This will give me a parallel programmed web server every single time a request comes in, even if there are two requests that come in at exactly the same moment. The first one's going to get launched, the second one's going to get launched, and they're going to run in parallel. If I have two processors, I'm going to be able to run them just perfectly parallel. That is super, super easy in the grand scheme of things. To go from I have a web server that receives one request, tells everybody else to shut up, finishes sending it, and then receives the next request, to this, I literally had to change like 3 lines to create a new thread that says, okay, given this one file descriptor, read and write from it until you're done, and then just exit. And I'll make more threads when I get more requests. That's a really basic, really easy way to do this. That's useful. But what happens behind the scenes here is that the operating system is going to put your program to sleep, wake your program back up, and it's going to interleave different requests for you. So if I had 2 different requests, it's completely okay for them to be interleaved because they don't touch each other in any way, right? One of them has its own file descriptor, other one has its own file descriptor. They don't interact with each other in any way, so any interleaving is fine. The important part here is that the operating system and the idea of a stack frame and local variables is making it so that when you do something, like you spend a few microseconds doing some operation, then if you get swapped out, we swap somebody else back in. And what they fundamentally have is the state that they are in going through this function, right? It's a little bit complicated, but stick with me. The state that they're in is like how many bytes they have in the buffer, whether they've opened that other file yet or not, whether they're receiving a file or sending a file, what file it is that they're sending. All these different things are important components of keeping track of where you are in that program. We as programmers have been doing this for a few years, many decades in my case. We don't think about the fact that I set a variable in the first line, and the next line, oh, it's just there. Even if I got swapped out and then swapped back in again, all of my state is still right there. So fundamentally, what the operating system is doing is it's kind of saving your place for you within a protocol and then doing other things at the same time. When they're isolated from each other by being in different stacks and different threads and different processes sometimes, means that you don't have to worry about any of that isolation yourself. But it comes at a cost. You're vulnerable to the preemptive multiplexing. So what this fundamentally does is threads and processes are typically used for preemptive multitasking. So preemptive multitasking is tricky because at any moment in time I could get pulled off. That's the downside. And so I have to coordinate between them. The upside is I don't have to worry about keeping track of where I am. I just kind of get to keep track by default by writing that thread as if I'm the only one that's handling this request, which you are. The other downside is that switching at any moment in time is a little bit bad for performance for a variety of reasons. One of them being when you have more threads, you have to use more memory for those threads. There is overhead to do the context switch from one thread to another. If you're going to create new threads, that costs extra time. If you really wanted to make your program as fast as it possibly could, what you would want is to say, listen, I know what needs to get done at any given moment in time based on what information came in. I'm going to handle all of this multiplexing of different requests myself rather than rely on the operating system to keep track of it for me. So what I would end up needing to do is say, what are the events that could block waiting for I/O? So receiving the request can definitely block waiting for I/O. Opening the file can also, like opening the file can block. Reading the file that was requested, this can block. Writing the HTTP response header, technically this can block, although it's relatively uncommon. Writing the file that was requested also definitely can potentially block. All of those things need to be split up into one discrete group of things done by CPU instructions and say, okay, when I have received new bytes from the client, here are the specific things that I'm supposed to do. Or once I have gotten an entire request, I can interpret it using CPU instructions, right? Library calls, whatever have you. But once I figure out what file to open, that's going to take a little bit of time. I can create that file descriptor, but I've got to wait for the operating system to say, hey, that file has been opened successfully, and that might take a little bit of time. So I'm specifically going to say there's a whole bunch of things that happen here between receiving the request and opening the file, because opening the file causes like a substantial delay if you're opening a file like on a spinning disk. Reading the file in might take a while, writing the response header might take a while, and then writing the file might take a while. So what I need to do is I need to split this entire protocol up and say, which state am I in? Am I in state A, waiting for the request? Am I in state B, waiting to open the file? Am I in state C, whatever have you? And then based on where I am, an event will happen. Like the event that happens is the file opens successfully. So I say, okay, well, if I was in state B, waiting for the file to open, and the file opened successfully, so I need to change this specific conversation over to being in state C, and then I need to do whatever I need to do, like start reading the file. But as soon as I say, oh, I need to read this file, I'm going to say, okay, well, I'm going to put this file descriptor in the read set, and I'm going to go to sleep. So that if bytes come in, I'm going to say, okay, I'm in state C. I received some bytes. Did I read the entire file in this case? If I did read the entire file, okay, great. I can actually move down into state D. But if I didn't read the entire file, I need to put what I got into a buffer, put myself to sleep by saying, okay, I'm done with this iteration of the event loop, and wait for new information to show up on that file descriptor. So when I receive that new information showing up on that file descriptor, I'm going to say, okay, I'm in state C, I received more bytes, and this is a full valid file. I just received a 0 on a read. That means I got to EOF. That means I'm done with being in state C. I can move on to state D. So you need to refactor that so that every single step of the operation happens in its own iteration of the event loop. And the structure that I gave you for homework 6 more or less approximates that. Halfway decent, so you don't have to do too much of this design yourself, but it does put you through the motions of creating a stateful protocol and moving it through those different states. So that's the main differences here between process-based, thread-based I/O multiplexing. Process-based and thread-based, you don't really have to rewrite anything. You can imagine, you can pretend you're the only one running, and the operating system is what allows you to save state kind of transparently. An I/O multiplexed concurrent programming regime gives you much more performance, but it's much harder to write because you just got to refactor the entire thing. There are cool primitives I was talking about earlier, like await and async, where you can say, I'm going to have the language runtime keep track of where I am in one run of a protocol, but I'm actually going to switch between them. And that makes things much more efficient. You kind of get the best of both worlds. It's easier to program, but it's also faster because it's doing I/O multiplexing. Anyhow, that's what I have today on concurrency. Thanks so much for watching, and I'll see you sometime, hopefully soon.